Alright guys, so picking up where we left off, just kind of as a refresher, we are working on 2013, A, number 1. We've done through question 1A at this point in time, which basically was trying to determine the Ksp value and working through the amount of MgF2 that dissolved based off of given a concentration of fluorine ions. So if you remember, we kind of walked through it that way. Okay, and then we started on question B. In question B, we're looking at a solution that contains both calcium and barium, and we wanted to know which one's going to precipitate first. And we decided that it was going to be the one with the lowest Ksp value, because it's going to reach Q first, causing a shift towards the reactants, causing the solid to form. So that would be calcium fluoride. Let's keep going down and looking at the rest of this. Okay, so they kind of just make a note here saying that the volume change due to the NaF solution is not significant enough to affect our total volume. So we're going to ignore that right now. That's not going to play a huge role, but it will in a little bit. And we're going to go down to 2, and it says calculate the minimum volume of, or the minimum concentration, sorry, of fluorine necessary to initiate precipitation of the salt selected in B1, or the salt selected in B1. So our salt we selected in B1 is this guy right here. And it wants to know how much fluorine is going to be required to cause a shift in that direction. In other words, what we're really looking for here is, in our ICE table, our equilibrium value of fluorine. Because once that equilibrium value of fluorine is hit, we're going to see that shift towards the reactants, and therefore the precipitation start falling out. So let's kind of look at that. We have CaF2 forming calcium ions and 2 fluorine ions. And we're going to basically work through an ICE table. We don't care about the calcium fluoride. Again, it's a solid. And, we don't have 0 calcium. If you remember back to looking at the original solution. If you go back up here, we already have some calcium already in solution as we're adding the sodium fluoride. So kind of think of it as the common ion effect to some extent or another. So we already have 0.10 here and 0 fluorine. So plus x plus 2x, 0.10 plus x, and 2x. And again, 0.10 plus x is going to be very small, so we can kind of assume x is negligible. So solving this out, we need our K value. K values up here is 3.5 times 10 to the negative 11. And that's going to be equal to 0.1 times 2x. And remember, this is squared. So we go through and we divide by 0.1, and we'd get 3.5 times 10 to the negative 12. We're then going to take the square root and get whatever that concentration is, because that's a concentration of fluorine. So when we take the square root, we're basically going to get 2x is going to equal 1.9 times 10 to the negative 5th. Okay, and what that's going to be, remember 2x is the fluorine ion concentration, so fluorine ion concentration is equal to 1.9 times 10 to the negative 5th. We're not actually solving for x, because what we care about is this right here, which is equal to 2x. So once this concentration is reached, once this amount of fluorine ions is added from the sodium fluoride, we're going to start seeing that shift towards the reactants, and therefore we're going to start seeing the solid calcium fluoride being formed. So really what this is just asking is how much fluorine is going to be in solution at equilibrium. I know it's kind of asking it weirdly, but that's basically what it is, because again, once this value's hit, it's going to stay at that value because of the shift towards the reactants. Think of your Q versus K. Okay? All right, then it says calculate the minimum volume of the sodium fluoride that must be added to the beaker to initiate this precipitation. So here's kind of the idea here. We know we require this molarity of fluorine ions in our 500 milliliter solution. And remember back up to that weird statement at the beginning, it says to assume the total volume of the beaker, the 500 milliliters, is not affected by the additional volume of sodium fluoride. Why is that important? Because now we can do the math. If we know this is our molarity of fluorine in our 500 milliliter solution, because the amount of sodium fluoride is not affecting the 500 milliliters, we can backtrack that to how much volume we need of this. So you can kind of do this one of two ways. I'm going to do it just following through the math, but you can also do it with M1 V1 equals M2 V2. Okay, because the amount of moles in both solutions are going to be the same. It's just in how much solution they're in. So let's kind of think of it this way. If our molarity, molarity equals moles over liters, is 1.9 times 10 to the negative fifth, that's going to equal x moles over 0.5 liters. So working through that math, we're going to get a x value, which is our mole value, of 9.5 times 10 to the negative 6, and this is our moles. So this is the amount of moles of fluorine that is in this 500 milliliter solution so that this concentration is reached so that we get the precipitation. So what does that mean for the amount of this solution that we needed to add? Well, let's think about it. If that's our molarity and this is the moles we need, we can now calculate volume. So if our molarity is 0.20 molar equals 9.5 times 10 to the negative 6 moles, we're solving for our liters here. So multiply by x and then divide by 0.2, or cross multiply if you want to think about it that way. There's a 1 down here, however you want to think about solving it. What we get for our volume is going to be 4.8 times 10 to the negative fifth. And this is in liters, so think about that in terms of milliliters. It would be 4.8 times 10 to the negative, just think about the math. 10 to the negative second milliliters, because you divide by 1,000. So again, this is why the 500 milliliters compared to the 4.8 or 0.048 milliliters that are being added is essentially still 500 milliliters, but they're still wanting to know how much we're actually adding before we see that precipitation form. So there we go. And the last thing is part C. There are several ways to dissolve a salt that has limited solubility. Describe one procedure to redissolve the precipitation formed in part B. Now, we didn't really talk about this much in class either, but I want you to use common sense with this one. When you are trying to make sweet tea, okay, and you're trying to dissolve a certain amount of sugar in there, what temperature is the tea typically? In a lot of cases, it's going to have to be hot tea to dissolve sugar. If you think about it, if you order unsweet tea at a restaurant and it has ice already in it, and you try to dissolve the sugar in it, it doesn't dissolve very well. Why? Because cold solutions don't dissolve, have a limited solubility. They don't dissolve as well, whereas a warmer solution will be able to dissolve more. So what's one way we could increase the solubility of this? We could heat up the solution. Okay. What's another way? And we did see this one in class. We can add more water. Okay, by adding more water, there's more space for the salt to dissolve. So think about it this way. Go back up here. Okay, if you add more water, you're decreasing this concentration, which actually makes Q less than K. So some of this salt's going to shift towards the products, therefore dissolving some of the solid to create the ion. So you could add more water to dilute it, and in the process of the dilution, it's going to shift to make more of the ions, therefore dissolving more of the solid. So those are two valid ways in which you could dissolve more of the salt. Okay, so that's kind of an interesting problem. This is from 2013, so it's a little bit older, but not really that old. I'm going to work through another one in just a minute for the next video. So hopefully this is helping, and hopefully the next one will help even more.